The most common HSC questions ask you to solve an absolute value inequality. This one appeared in last year's 2016 HSC in the first long response question about halfway through. Again, there are a number of ways that you can solve it, and whether you choose to do so algebraically or graphically depends on the way you like to solve these questions. But be careful if you are going to use graphical methods that you do so as accurately as you can. I'll show you both methods. Firstly, if we solve this algebraically, this is telling us that the absolute value of x minus 2 must be less than or equal to 3. But as that absolute value symbol means that it can take on a positive or negative version and still give the same result of 3, then we also need to solve for the negative version of that function to obtain both valid answers. Just like before, when we had the absolute value of 4 gives us the same result as the absolute value of negative 4, in this case, the absolute value of x minus 2 gives the same result as the absolute value of negative x minus 2. Now if we solve both of these equations, starting with the first one and adding 2 to the other side, we obtain that x needs to be less than or equal to 5, and remembering that if we do multiply an inequality through by a negative, which is what I'll do to begin solving this equation, we need to reverse the inequality symbol and then adding 2 to the other side, we get that x needs to be greater than or equal to negative 1 as well. If you do solve algebraically, you are required to check that these solutions are valid. This is most obvious when we consider the graph of this inequality. Essentially, the inequality is asking us to look at all of the sections of the graph where y is equal to the absolute value of x minus 2 is less than or equal to the graph of y is equal to 3. Producing a quick sketch of both of those functions, y equals the absolute value of x minus 2, where the minus 2 is inside the brackets, we now know shifts the absolute value function to positive 2 on the x-axis with a gradient of 1, and will therefore cross the y-axis at 2 as well. On the right hand side, we have the line y is equal to 3, which is a horizontal line sitting through 3 on the y-axis. You can see that these two values that we've identified algebraically are the points of intersection of our two graphs at -1 and at 5. And the inequality is asking us to identify the section of the graph where the absolute value function is less than y equals 3. So we're looking at all of the values where the absolute value function sits below the line y equals 3, which is occurring between the values of x equals -1 and x equals 5. We can also check this algebraically by having a look at a value that sits between them, such as x equals 0. By substituting it into the original equation of the absolute value of x minus 2 must be less than or equal to 3, giving us the absolute value of -2 is less than or equal to 3, and by taking that absolute value we get a true statement of 2 is a value less than or equal to 3, meaning that 0 works, it is a valid value, and hence my inequality solution must lie between -1 and 5 and all of the values between it. The last question I'm going to show you is a challenging question that appeared in the 2013 HSC paper. It's quite near the end at question 15C, and it did challenge a lot of students in that cohort. For the first part, we can see that again they've asked us to sketch an absolute value function, but this time not only have they shifted the function to positive 3 on the x-axis, they have also changed the gradient to 2. So that is going to affect how far you shift your graph. The best option here is to work the algebra and substitute in y equals 0 to obtain the x-intercept. So solving our absolute value for 0, we obtain an x-intercept of 3 on 2 or 1.5 as shown on the graph. Thinking about the y-intercept, which occurs when x is equal to 0, we can see that that will negate the 2x section of our absolute value function, and then we take the absolute value of the remaining negative 3, giving us a y-intercept of positive 3 as shown on the graph. So the first part was fairly straightforward, but as you can see, this time it was only worth 1 mark. The remainder of this question is the more challenging part. They've asked us to use the graph obtained in part 1 and find all the values of m being the gradient of a linear line crossing with a y-intercept of positive 1, which is marked on our graph, where that line will have exactly one solution when it is solved against the existing absolute value function that we've been asked to graph in part 1. This means that if it has one solution when you equate them to each other, that they will intersect at one point only. So we are looking for any valid gradients that mean the lines touch each other at one point but don't physically cross each other any more than that. Our line must always go through the y-intercept of positive 1. So for any gradient we're considering, we're drawing lines that must cross through that point and just changing the steepness to allow this new line that we're drawing to only cross that absolute value function at one point. Probably the most obvious one is the line that will touch at the same x-intercept. It'll have a negative gradient as it has to pass through 1 on the y-intercept. And we can solve for this gradient value by considering that rise of 1 over the run of 1.5. And that gives us our first valid gradient, remembering that it is a negative gradient as the line is heading downhill, of negative 2/3. However, this isn't the only gradient that is going to give us exactly one solution. Let's consider a parallel gradient. If we give a gradient of 2, remembering that it must still pass through 1 on the y-axis, running parallel to the absolute value function means that it will only cross at one point, and it's never going to cross this parallel line as it's running in conjunction with it. So again, this gives us another valid gradient of positive 2. Now, if we make this gradient more shallow, remember that that will draw it down towards the x-axis, meaning that eventually that line will cross at a second point. So that is not a valid solution. However, if we go the other way and make the gradient more steep than 2, then we're moving the line closer to the y-axis and hence further away from the other area of the absolute value function that we would be crossing. And so this also gives us a valid gradient, whereby the gradient must be equal to or larger than 2. So we're almost finished. The last gradient we need to consider is the reverse of that, being -2. So remember that it still must cross through 1. So if we set a gradient at -2, this particular line will never cross the function as it's running parallel to the reflected part of our absolute value function. But if we make that line a little bit steeper and therefore push it towards the y-axis, then it will cross that reflected section at some point. So to make this gradient steeper, we need to increase the magnitude of the number, meaning that it needs to get more negative. So while it can't equal -2, as this just gives us another parallel line that will never cross, it can be less than -2. And this gives us our final solution for 2 marks, that the valid values of m, or all of the valid gradients, are the original one we found at -2/3, that m can be greater than or equal to the parallel gradient of 2, and that m can also be less than a gradient of -2.